Let's begin a discussion about polyprotic acids and how they dissociate in a stepwise fashion. We know that polyprotic just means many protons, many hydrogen ions in a formula. Just to kind of remind ourselves of some vast notes, monoprotic, an example might be HCl, a single proton in hydrogen chloride. A diprotic acid, something perhaps like carbonic acid, H2CO3. And a triprotic acid, H3PO4. Mono, di, and triprotic are really just reminders of how many hydrogens are involved in our particular acid. So when we say polyprotic, we just mean more than one. What we're seeing is that polyprotic acids always dissociate in a stepwise fashion. So I'm going to write dissociate stepwise. In other words, we always take off one hydrogen at a time in a dissociation equation. The first hydrogen ion comes off significantly easier than the second. The second would come off a little bit easier than the third. We denote the stepwise fashion of a polyprotic acid by saying Ka1, the acid dissociation constant for the removal of the first proton. Ka2 would be the acid dissociation constant for the removal of the second proton. And if there is a third, Ka3, the removal of the third proton. It's always easier to remove the first and the second than the third, so the magnitude of the Kas becomes successively smaller. Removal of the first, second, and third proton increasingly becomes more difficult. So the Ka values become significantly smaller as you consider the ease at which the protons dissociate. If we were to consider really just thinking about a stepwise fashion, let's take any acid we'll just make up on a diprotic acid, H2X. Whatever X might be is just the negative ion for our acid. In a dissociation equation, just to kind of illustrate with exaggerated arrows, the removal of the first proton, H+, leaving us HX negative. The removal of the first proton would have a Ka1 value. And what I'm trying to show is that this removal is easier than the successive. So let's take, just to remind ourselves of some conjugate pairs, we would know that this would actually be in water. And so we would label this the acid. Protons are always acids, and this would be the base in conjugate Bronsted-Lowry pairing. But this base in the first equation now becomes the acid in the second equation, and I'll take off that second proton. And again, I'm going to show this with exaggerated arrows to say it's not as easy to take that off. So if I'm removing the first one, whoops, I want to exaggerate this way. I want to say that most of it is staying in its molecular form here, taking off the second proton, going down to the anion of -2. So I'm really stressing that I'm favoring the left side of this equilibrium, partial removal, very difficult. So this expression, Ka2, is much smaller. And I'll just write significantly smaller than Ka1. This would be a little bit larger in terms of just the magnitude of the number. So the base in the first step, right here, becomes the acid in the second step, removing the proton. Typically, we're seeing that a magnitude of 10 to the third power or more to get off that second proton from a polyprotic acid. Therefore, all of this is just saying the following. The removal of the first proton is really all we ever need to consider when we're asked to calculate the pH of a polyprotic acid. Considering only Ka1 is all we need to calculate the pH of a solution. The pH of a polyprotic acid is determined from the Ka1. That this value of the hydrogen is so insignificantly small that it's really not contributing to the overall amount of protons in the solution, which affects the pH. Remember, that's what pH is measuring, the power of the hydrogen ion, negative log of that molarity. Since this is significantly small, a negligible quantity, we disregard it and calculate pH just from the Ka1 dissociation. Let's talk that through with an example problem. The solubility of carbon dioxide in pure water at 25 Celsius, 0.1 atmosphere pressure, is given to us as 0.0037 molar units. The common practice is to assume that all of the dissolved gas is in the form of carbonic acid. Let's put some chemistry to that and write the equation. This is a combination, and it is a helpful hint that we once learned the pattern of chemical change combination. The helpful hint we learned back in first year chemistry, when a nonmetal oxide combines with water, it forms an acid. Alrighty, so just an old combination reaction. The nonmetal oxide here is carbon dioxide. If it's being bubbled into water, we add water to its formula. Start with the H's and we end with the O's and simply add them up. We are going to create carbonic acid. In a combination reaction, just simply blowing into water from a straw, you're putting carbon dioxide into some water. We are producing an acidic solution. The production of carbonic acid, and now we're saying that this molarity is 0.0037 molar. Let's calculate the pH, and they give it Ka1 value, and they give us a Ka2 value, so we don't need our Ka chart to look them up. They are provided for us. So let's take a look. I'm going to put some paper down here so I can write a little bit bigger. I have the following equilibrium. Carbonic acid was produced, but when I consider calculating in terms of the acidity of our solution, I'm thinking of dissociation. In other words, the release of the ions in a stepwise fashion. Carbonic acid will dissociate to release a first proton, H+, leaving us the negative ion, H3O3 negative, the bicarbonate ion. This is our acid. Water over here, if we were to consider water, I could add there, this would be our Bronsted-Lowry base. And if I add the water, remember we're really making hydronium, H3O+. So without the water, I'm just showing hydrogen ions, or with the water, we produce hydronium ions. But you can see that this is the conjugate acid being formed, and this would be the conjugate base. So just some Bronsted-Lowry acid-base reminder. The Ka1 given to us for this expression was 4.3 times 10 to the negative 7th, just a number, no unit associated. So in the first expression, here's what we know. The concentration, 0.0037 molar of the acid. And when I dissociate, I release equal amounts of the hydrogen ion as bicarbonate ion. I'm going to let X represent the first proton and the equal amount representing the negative ion of bicarbonate. And we'll set up our expression. Ka we know is an expression that compares the molar units of hydrogen ion times the molar units of the bicarbonate ion all over H2CO3, the original molecular form of the acid. We have what we need to plug in. We have our Ka value, 4.3 times 10 to the negative 7th. We said let's let hydrogen represent X, and also the bicarbonate is X, so I'll simply write that as X squared over 0.0037 molar. Just to remind ourselves how to pull out X, X will be the square root of the product of 4.3 times 10 to the negative 7th times 0.0037 molar units. I have to pull out the square root so that I can find the value of x. And let's hit that. 4.3 e negative 7, cross multiply with 0.0037. I will square root my answer. And the value of x, which is the proton concentration, is 3.99 times 10 to the negative 5th molar units. Knowing that pH comes from the first dissociation only, pH for polyprotic acids is solved from Ka1 chemistry. Just a little reminder there. The Ka1 calculations are the significant production of the hydrogen ion. So pH now is simply found by taking negative log of our hydrogen, 3.99 times 10 to the negative 5th molar units. And so while that's still on our calculator, negative log of answer, and we get 4.40, 2 decimal places for pH, 4.40, the pH of our solution. On the opposite side of your paper, this problem continues. This is a next bullet before I want to end. It asks us to calculate the carbonate molar concentration. So I'm going to work right here, but I'm going to continue on my workspace. All right, so this is in the notepad where I am now working, top of page 10 in our notes, but I'm just going to continue on my same work page, and so you can just flip over and keep going with me. Notice that we've taken off one constant so far, one hydrogen ion with a Ka1 value. What we're being asked to do is take off the second proton and find carbonate. So remember how this conjugate base in step 1 becomes the acid in the second dissociation. So let's take off, I'm drawing those arrows better this time, the second proton, and knowing that the removal of the second proton gives us something known as Ka2. And Ka2 is provided for us in that original reading. So if I just flip my page over again, see here, 5.6 E negative 11. Alrighty. So what do we know? We want to know this concentration. That's what ultimately we're being asked, isn't it? To know the bicarbonate. What we just solved for actually is up here, if you remember what X stood for. X stood for the hydrogen ion, and it stood for the bicarbonate ion. This value for the hydrogen is also, just remind ourselves, the bicarbonate. They were indeed the same number. So I know these two values from the previous calculation. X stood for the molar concentration of hydrogen, and it stood for the molar concentration of the bicarbonate conjugate base. What I don't know is the X, but I can easily solve for that with a Ka2 expression. Ka2 is equal to the molar concentration of hydrogen ion times the carbonate ion set over the molar concentration of the bicarbonate ion. We know the following values provided in the question. Ka2 was 5.6 times 10 to the negative 11th. The molar concentration of hydrogen, 3.99 times 10 to the negative 5th. We're looking for carbonate set over the molar concentration of the bicarbonate. And look what's happened to the math here. Ka2 set equal to the concentration of product over reactant. These two simply cancel though. they simplify to where now the value of Ka2 is indeed equal to the molar concentration of X, which we let stand for carbonate. Here's what we've discovered. pH of a polyprotic acid is always found by just simply using the Ka1. But if we have to go on to solve for the negative ion in any successive step, we know to use the Ka1 concentration of hydrogen ion through every stepwise ionization thereafter. What's unique about a Ka2 is these two would cancel, and Ka2 becomes the direct molar concentration of carbonate. If there were a third step in a polyprotic acid, removal of a third proton, let me just kind of give a side note, and I'm going to flip my paper over. This would be an excellent margin note. Let's suppose, and I'm just going to pick probably the most common polyprotic, phosphoric. We know that step 1 would remove the first proton, giving us the negative of H2PO4, negative 1. This is what's called Ka1. That then goes into a stepwise ionization, removing the second proton. A little bit more difficult and reminding us of the magnitude here. This is Ka2. And if indeed we want to take off that next proton, HPO4 negative 2, very difficult, H plus and PO4 negative 3 would represent the ionization of Ka3. The first ionization is used to calculate pH. Because these are so insignificant, they're so small in comparison to this magnitude, we just disregard those values. But once I solve for X with the pH, this concentration of hydrogen ion from the Ka1 calculation is now a known quantity carried through every successive calculation. So if indeed we were targeting this molar unit, we would know H plus every time we set up a Ka expression from the calculation of Ka1. You are now ready to begin some homework, assignment number 5. Good work today.